Hello. The previous video has discussed the one example scenario of the AI algorithm solving the problem of censoring case, and this video will discuss one more example of using EM, which is to solve the mixture distribution estimation. The problem is we have two random variables and our supposed distribution, and we further have a we further have a latent variable wi that follows the Bernoulli distribution. If it is 0, it's from f1, and if it's 1, it's from f2. And in some scenarios, we don't know whether we don't know the exact success epsilon of this Bernoulli random variable, but sometimes we know that, and this problem that just suppose we don't know the exact probability of coming from a distribution, and we want to estimate this mu and epsilon and further the epsilon. And why this is necessary? Because it's often used in clinical trial, especially in the period of double-blind experiment. The statistician researcher don't know whether this kind of x1 x2 x is from placebo group or drug group. We don't know that. It's double blind, right? And but we want to know the effect of the drug, so we suppose they follow S1 and F2, and we suppose this P and 1 minus P, and we want to estimate this distribution and then compare the difference of these two distributions to, and this one is from, maybe this one of them is from placebo and the other is from drug, and then we could do the further experiment, further statistical research, and it's just a very simple, not simple, just basic things, but it has more complex in the real clinical trial. Now let's focus on how to solve this kind of a problem. But since our PDF that our likelihood could be written as this, but in the EM algorithm, what we want to write is the complete likelihood, and in that case, we want to know the PDF of fxw based on the conditional probability. We know this is true, right? And this is just the Bernoulli PDF. We know it's either epsilon or 1 minus epsilon or epsilon if wi equals to 0 or wi equals to 1. And this is just fx1 wi equals 0, f2x, f1x, fi equals to 1, and we just know that equals to 1 minus epsilon f1x if wi equals to 0 and epsilon f2x if fi equals to 1. And actually, this is not true. We just write yeah, this actually the LC theta x w, and we get that, but we also should add one epsilon, which is不冷。
啊，你那么转我特别好，这么着。
What is that?
典雅高贵，美丽动人。
And I'll further. Now we want to take the expectation of this wi, this random variable, because we want to use it in the q function, and it's very desirable to mention that this wi is random variable that is discrete, so we shouldn't take the integral of it like the past example. It's an awkward mistake that I have taken in the past times, and so we should use the summation instead of integral to do this expectation. In that case, what we want to know is just right here. Take the conditional expectation. It's like k w x no, it's k w theta x equals to k x w theta over just h and g x theta, and this is a likelihood function, and this is a complete likelihood function. And here wi equals to and this is what we write here. But here we only want to know, here we want to only care about wi equals to 1, and here also wi equals to 1. So this is, we just multiply this, which is and here the observed likely function is not relevant to w, so which is here. We just do the multiplication of since And since this is really like it is the term that we only choose the group that xi equals to 1, but also we times many terms times 1 if this wi equals to 0. So this has n terms, and this also have n terms. And it's just the same idea as before. These terms are independent. So we just could write down equals to here I just forgot to add this addition because this does a PDF, which is that, right? And here, which is just what we want. Or we could say this is just the whole probability, and this is just the conditional probability. And it's also easy to intuitively thinking using the Bayesian theorem, right? Yes, just two ways of thinking. And we write down the Q, and since we have replaced the previous W to be the its expectation, right? And here we also show the estimation of the term, that which is that. I will not write down here. And here we just take a partial derivative to maximize its Q. And also, what I want to mention here is the estimation of epsilon. One way is to take partial derivative with respect to P, which is that just the epsilon, which is just and they have the so we have but here is just not the Wi but the gamma, because in the Q step we have replaced this gamma with as W, so it actually here I write mistakenly, it's just a gamma. Or we could estimate this epsilon using the MLE of Bernoulli, which we know is just this. right?